So far, I've alluded to this difference between covariance and correlation PCA. Here, we're going to explore it a little bit closer. Principal components can be done using eigenvectors of either the covariance matrix or the correlation matrix. The default in SAS is the correlation. The default in R is the covariance. For most packages, you have to check. Now, if you recall, the correlation matrix is simply the covariance matrix of the standardized data. So the question of when to use correlation and when to use covariance really boils down to the same question of when should I standardize my data? So in covariance PCA, the data is centered. It's essentially unchanged. It's just a translation so that the center is the origin. And then those directions of maximal variance are drawn. So we should use covariance PCA when the scales of our variables are not very different. Now, there are many instances where this is the case. In genetic analysis, in a lot of image analysis, Likert scale response analysis, oftentimes you have a fixed scale on which the variables can be. On the other hand, correlation PCA is a situation where your data is standardized before those directions of maximal variance are drawn. So we want to use correlation PCA when the scales of the variables are very different. And I frequently get this question, well, why wouldn't we just always use the correlation matrix? What could it hurt? Unfortunately, there are a lot of people in industry and even academia that agree with this thought. I will argue, as well as some very classically trained statisticians, that correlation is really a brutal standardization that we put on our data, because we make every single variable have the same amount of variance contained in it. And there are situations where we may not want to do that. I'm going to show you an example of such a situation where, just from our own knowledge of the data, we should realize that standardization is not the approach that we want to take. You may not be able to see enough of a difference in the output to feel convinced, but I assure you it's because this is an illustrative example. It's not a practical one. 5 variables are not likely to be reduced via PCA. All right, so in this example, I have scores for 100 students on 5 tests. Now, I'm going to take you into VIA, and we're going to take a look at what that data looks like. So first of all, you'll have to define your CAS libraries. And then in the public data set, you should see this test scores data. You'll see test 1, looking down the column of these 100 students, it looks like everybody did very well. Test 2, on the other hand, well, there are some problems. Test 3, same thing, there are some issues. Test 4, also some pretty big issues. Test 5, looks like maybe that test, all you had to do was spell your name right, and you got a 98. We can look at some of the summary statistics for that data set. In fact, I think we'll get some with the proc print comp procedure. Let's see. So this is proc print comp. I'm telling it what data to use. I'm specifying an output data set. That's where SAS is going to put the scores. I'm telling it to use all of the variables in the data set, test 1 through test 5. And then at the top, as I had hoped, we get the simple statistics. So you can see the means of the 5 tests are quite different. Looks like test 1 and test 5, all students did very well on. Even the standard deviations are very small. So it looks like just about everybody got an A on test 1 and certainly on test 5. Test 2, 3, and 4 were much more difficult. Much larger amounts of variance, much lower means. Here I'm given the correlation matrix, okay? And now it says eigenvalues of the correlation matrix. Again, the correlation is default in SAS. So now we can answer some questions. If I asked you, what is the variance of the first principal component? The variance of the first principal component is 2.58, because again, the eigenvalues give variance. Now, what proportion of variance is explained by the second principal component taken by itself? That would be 0.20. Now, how much variance can I explain with 3 principal components altogether? Together, the first 3 principal components explain 90% of the variance in the data. The next piece of output is the eigenvectors. So the eigenvectors, again, these are the loadings. Prin1, the loadings for principal component 1, looking down this list, it looks like it's primarily those middle 3 tests. And that is what I would expect to see, given that those 3 tests had the largest amount of variance. However, on the second principal component, those middle 3 tests are not highly weighted. Instead, I get test 1 and test 5. Moving further on, I start to see some of these other differences between the test scores. But I can use these loadings to help me understand the scores in context. And we'll do that here in a minute. The final piece of output is just a plot of these eigenvalues. So this first column here, 2.58, that would be this first value on the scree plot. And this is supposed to help us choose a number of components for dimension reduction. Again, we're going to take this with a grain of salt. We only have 5 variables. The goal here may not necessarily be dimension reduction, but just to get a view of the data in 2 dimensions. We can do that by plotting the scores. So I'm going to look in the output data set I just created, these test PCs, see my original data is given, and then I get the scores for each observation along each component. So this is really, if I take all 5 principal components, I haven't done anything. I've just rotated the axes to one that's more complicated to explain. But I can use it to project the data onto the first 2 components just by dropping the last 3. So the next procedure here in my code is this SG plot, where I'm making a scatter plot of principal component 1 and principal component 2 from that output data set. Okay, and so this is the projection of my 5-dimensional data onto a 2-dimensional plane that has the most amount of information possible. Now, if you look at this closely enough, you may see it looks like there's kind of a dividing line right here. That's true enough. Let's look again at the loadings. So I have to run that code again. And talk about how we might interpret what's happening here. So again, remember that the scores or the coordinates of each observation will be formed by taking a linear combination of their test scores using these weights. So for observation 1, the coordinate along principal component 1 is pretty much an equal weighted sum of those middle 3 tests. Now, granted, I would also be subtracting some of test 5 and adding a little bit of test 1, but the main driver of that score along principal component 1 are those middle 3 tests. So someone who performed very well on those 3 tests is going to have a high score for principal component 1. This is something that we can verify in the data. If we actually look at this data set, maybe we can sort. Yes. So this individual had the highest score for principal component 1. You'll also notice he or she aced nearly every single test in the data, especially those middle 3. Okay, the next highest score also did very well. And as you scroll down this page, you'll see the students who performed best on those middle 3 tests. And as you go to the bottom, you're gonna find the people that scored the worst on those middle 3 tests. So principal component 1 serves as this like simultaneous sorting mechanism to sort my students according to their performance on the middle 3 tests together. Okay, and those in the middle may have done well on one test and not so well on the others. If we go back to these results, the second principal component, you know, I'm gonna take these small numbers and I'm just gonna like ignore them in my interpretation. And that means that principal component 2 gets at test 5 minus test 1. Now again, these are not exact interpretations. This is not a 1, these are not zeros, and this is not a 1. But it gets at the difference between the score on test 5 and the score on test 1. So if someone's principal component 2 score is really high, it means that they must have done very well on this and very poorly on this. Because again, poorly, that's going to be below average. In centered data, it's going to be negative. So I'd be taking a positive number times this, a negative number times this, and that's going to give me a large positive number on principal component 2. If I'm to look here and I sort, the largest score on principal component 2 is someone that got a 100 on test 5 and did not do as well on test 1. And it's probably essentially going to be mostly about test 1 because there was such little variability on test 5 that everybody got above a 98 almost. And so as I go down to the bottom of this data set, I see that these are the people that did better on test 1 than they did on test 5. Up here, these people did better on test 5 than they did on test 1. So I can use those loadings to help me interpret what I'm seeing in my scatter plot. If I recreate this scatter plot, I guess I should just create it all at once. I know that the people to the right, higher scores on Prin 1 did better on the middle 3 tests. Those that did better on Prin 2 did better on test 5 than on test 1. But here's the thing. I don't really care about test 5 or test 1. Test 5 and test 1 had such little variability, they don't have much consequence to my practical analysis, especially for this example where I'm talking about test scores and I'm trying to differentiate individuals. This is a product of using correlation PCA. Because I'm insisting that each test be forced to have the same amount of variance. Because once you standardize a variable, you have a variance of 1. And so every test in the standardized version has a variance of 1. I can alter this by adding the covariance option. Now I'm given the covariance matrix, the eigenvalues of the covariance matrix, and now, interestingly enough, how much variance can I explain with 2 principal components? 98%. And coming down here, now I see Prin 1 is very much so a weighted sum of the middle 3 tests, because the test 1 and test 5 coefficients go down to something much closer to 0. And in the second principal component, test 1 and test 5 stay near 0, because those are not dominant directions of information. Instead, what it uncovered was a dominant kind of theme here, a dominant trend of information is that some students did better on test 2 than test 3. So if I were to give meaning to principal component 2 here, it would be the difference between test 2 and test 3. And those with large scores on Prin 2 here probably did better on test 2 than they did on test 3. Again, let's confirm that here. Let's make sure it opened the most recent version of this. So I'm going to sort in descending order on Prin 2. And yeah, this person got an 87 on test 2 and a 25 on test 3. 90 versus 30, 86 versus 29. And if I go all the way to the bottom to the smallest coordinates on principal component 2, I see an opposite trend. This person did much better on test 3 than they did on test 2. Likewise going up. Prin 1 still has the same meaning, but perhaps even more so. The largest coordinates did the best on the middle 3 tests, and the lowest coordinates did the worst. When I look at the scatter plot here, it's actually a little bit more, quite a bit more clear that I have a cluster of individuals over here. All of these did better on the middle 3 tests than the rest of the class. But for the rest of the class, I learned this additional piece of information that's actually rather useful, that these students did better on test 2 than they did on test 3 at the top, and these students down here did better on test 3 than they did on test 2. So while that's a simplistic example, it's a very good starting place, and I encourage you to look at this output and this data set thoroughly. Because if you're able to explain everything that's going on in this data set, then you really have what it takes to employ principal components in a more complicated scenario. Thanks for tuning in.